Unit Overview. This unit provides an introduction to data structures. The fundamental concepts and principles presented here are applicable to the main themes covered in the subsequent units. The unit begins with an overview of data types. It then discusses the distinguishing features of data structures and their organization. Finally, the concept of abstract data type is introduced. It is also explained how abstract data types promote the principles of software engineering and object-oriented programming. Objectives. After completing this unit, you should be able to understand the concept of data structure, distinguish between data structures and data types, learn how data structures are organized in computer, describe the characteristics of common types of data structure, understand the concept of abstract data type, describe the advantages of abstract data type. In computer science, data structure is a study of various ways of organizing data in a computer so that it can be used efficiently. Invariably, the information contained in a data structure is manipulated by a systematic and step-by-step process which is called algorithm. The manipulation of data structure may involve such operations as adding an item, searching for a particular item, deleting an item, rearranging data items in different ways. Thus, data structures and algorithms are closely linked together and play a complementary role in many applications. Over the years, data structures have gained significant importance because of their usage in several disciplines. Data structures are an integral part of modern operating systems, compilers, database management systems, data communication, and system software. Likewise, algorithm together with associated data structures have widespread use in several applications, including image processing, digital signal processing, simulations, numerical computations, cryptography, data compressions, and genetic studies. In this introductory unit, we shall introduce basic terminologies and concepts concerning data structures. Data types. All programming languages provide some built-in data types which are useful for efficient coding of programs. The predefined data elements are separated into two classes which are known as primitive and composite. A primitive data type defines a set of values and operations that can be performed on these values. The familiar primitive data types are integers, real numbers, characters, and Boolean, which are supported by almost all programming languages. A Boolean type can have only two values, true or false. The basic operations on these values are AND, OR, and NOT. An integer type can assume different set of values depending on implementation in a particular language. The set of basic permissible operations on an integer type are, for example, arithmetic operations and comparisons operations. The primitive data types are also called atomic or irreducible because these cannot be expressed in any other basic types. The primitive data types are always supported by the underlying hardware features and to a lesser extent by the compiler systems. This means that the range of values and the allowed operations depend primarily on the hardware circuitry. In general, the number of bits allocated to each type decides the range of values. For example, an integer type is often implemented using a 32-bit storage representation with 1 bit reserved for sign. In this way, the integer type can have a range of values over a billion. Characters are implemented by using 8-bit for ASCII and ABCDIC representation and 16 bits for Unicode. The later representation allows a range of values over 65,000 for encoding characters. The operations on primitive data types are often included in CPU instruction set. When such support is lacking, the compiler depends on built-in software routines. A notable example is the implementation of floating point operations. On small computers which do not have floating point circuitry, the real numbers are manipulated using software instructions. Of course, this approach considerably reduces the computational speed, often by a factor of 100 to 1000. Different programming languages provide a variety of primitive data types, which are identified by language-specific keywords. For example, Java defines 8 primitives. An important feature of Java primitives is that each data type is made up of a fixed number of bits, which is independent of a particular implementation. For example, an int type always consists of 32 bits and character of 16 bits on all platforms. C provides an assortment of primitive data types which are identified by the syntax int, float, character, double. The numeric type may be further qualified as short or long, signed or unsigned. C does not support Boolean data type. Instead, numeric 0 and non-zero values are interpreted as false or true. Further, the size of C data type varies with platform dependent. Visual Basic provides support for all basic types identified by the keywords integer, long, single, double, byte, and Boolean. The primitive types can be created as local or global, with each type preceded with the word public or dim. Composite data types are larger and more complex data types which are defined using combinations of primitive types. The common examples of composite types are arrays, vectors, and strings. An array is a collection of homogeneous data types. Almost all programming languages support arrays as built-in data types. We shall explain the detailed properties and uses of arrays in a subsequent unit. Vectors are essentially a mathematical representation of arrays. They differ from ordinary arrays in their implementation. For example, Java provides vectors as an array of flexible size. Strings are combinations of characters. The support for strings as a built-in data type varies a great deal with the programming languages. If string is defined as a primitive data type, string data is stored in an array of characters with a special delimiter. This is the approach followed by C, C++, Ada, and Pascal. In C, for instance, a string is represented as an array of characters with the null character in the last position. Fortran 90 and Visual Basic provide support for strings as primitive data type with associated operations of assignment, join, comparison, and substring references. In Java, strings are supported as built-in type of string class. Data structure. The built-in data types provided by programming languages are adequate for solving simple problems. In fact, all computer applications in early days depended exclusively on the built-in elements of the host programming languages for the storing and processing of different data types. This was particularly true of numerical or scientific-oriented problems. With the dramatic increase in the use of computers in various disciplines, it was realized that the primitive data types were not sufficient or powerful enough to solve advanced problems involving complex structural relationship among data items. The need for new data types was further exacerbated by the recent paradigm of object-oriented approach to problem solving. Data structures are meant to serve these needs. Simply stated, a data structure is a programming construct that stores a collection of data items. At first sight, data structures might appear as an extension of composite data type. This is true in a limited sense. Actually, there are two subtle differences. First, the term data structure encompasses composite data type defined in a programming language. It may even be a user-defined type to serve a particular application need. Second, and more importantly, a data structure implies some kind of organization or relationship among the constituent data items. For example, a character string, whether defined as an array of character or treated as primitive type, has a definite order of organized characters. An alteration in the order changes the memory and characteristics of the original string. On the basis of structural relationship, the data structures are classified into two types, linear and non-linear. A data structure which organizes data elements in a sequence, that is, one after the other, is referred to as linear. Array is a common example of linear data structure that exhibit linearity. Other examples are linked list, stack, and queue. We shall dwell at length on these data structures in later units. Here we briefly introduce these types. A linked list consists of data items called nodes. Each item contains an information field and a link field pointing to another data item. A stack is a data structure which works on the principle that last item added to the collection becomes the first item that can be taken off, like a pile of trays. It is also called LIFO, last in, first out data structure. A queue is a data structure in which an item can be added at one end and an existing item in the collection can be removed from the other end. It works on the principle FIFO, first in, first out. In a non-linear data structures, the relationship between the elements is more complex. It can be, for example, hierarchical, that is, one element may be linked to more than one element in the collection. Further, the linkage may be single or bidirectional. The nonlinear types are also referred to graph data structure. Common examples of nonlinear data structures are trees and graphs. A tree is a data structure consisting of a set of data items called nodes which contain an information field and linkage to one or more data items in a hierarchical order. There are several variations of trees. Some useful types are referred to as binary trees, AVL trees, red and black trees, splash trees, B trees, and heaps. We shall study their properties in a later unit. A graph is a set of data items called vertices or nodes connected by links, edges, or arcs. Operations on data structures. It should now be clear that data structure provides a logical relationship among the elements in a collection of data items. To be able to use these elements, it should be possible to apply some kind of operations to the data. First of all, we should have some mechanism to create a data structure and reserve storage in the computer to hold the data items. Also, once the data structure is not needed, it should be possible to remove the data items and release the allocated storage. Thus, creation and deletion are the two fundamental operations associated with any data structure. Other operations depend on the nature of data collection. Generally, the common useful operations include inserting, sorting, searching, merging, and traversing. Inserting involves adding a data item in a specified position to the data structures. Sorting consists of arranging the data items in specified order. Searching means finding a given data item in the data collection. Merging involves combining two sets of data item belonging to the same structure into a single set of items according to some defined criteria. Traversing means accessing each element of a data structure at least once. This operation is particularly useful on trees and graphs. It is also referred to as visiting. Undoubtedly, the strength of a particular data structure is determined, among other things, by the nature and variety of operations that can be performed on the data elements. User-defined data structures. The data structures stacks, queues, and trees described earlier are general-purpose data types. These are sometimes referred to as classic data structures. Because of their frequent use, some of the programming languages, such as Java, provide built-in support for these structures. However, we can also invent our own data structures to meet the specific need of an application. Such data types are called user-defined data structures. Suppose we want to store records of employees, each record consisting of employee's name, designation, and salary. We can define a data structure emp using cdata type struct and then create an array of employee data structure. C code for user-defined employee data structure is shown on the screen. The elements of employee data structure can be accessed using C's pointer notation. Storage structure. The data structure provides a logical view of the relationship among the data items. Storage structure describes how the data items are stored in the memory cells of a computer. In other words, the storage structure provides a physical view or map of how data elements of a particular data structures are allocated memory space. The elements of a data structure may be stored in computer memory in consecutive storage location or in disjoint locations. Each memory location is identified by a unique number which is called memory address. For example, the characters A, B, C belonging to same data structure might be stored in consecutive storage locations identified by memory addresses 1000, 1001, 1002 as shown. This arrangement enables us to access the elements rapidly. In order to retrieve the elements, we need to know the address of the first element in the data structure. The other elements can be accessed by simply moving to the consecutive memory cells. Alternatively, it is possible to store the characters A, B, C in non-contiguous storage locations. For example, A might be stored in location 2000, B in 3000, and C in 4000. However, in order to establish the relationship between A and B, we must provide information somewhere about the location of B. This information can be placed next to A. It is called pointer or link. Thus, storage location 2000 would contain character A. At location 2001, it would contain address of the character B, which is 3000. The arrangement is shown on screen. Abstract data types. An abstract data type is a relatively new concept for describing the internal organization and functionality of data structures. It is meant to combine the description of a data structure and the set of operations that can be performed on the data elements. More precisely, an abstract data type, commonly referred to as ADT, has the following characteristics. Number 1. It provides a description in terms of data types of all data elements that make up a collection. Number 2. It defines the relationship that exists between individual elements. Number 3. It groups together all the valid operations that can be performed on the data elements and parameters that can be passed. Number 4. It specifies error condition in particular operation, if any, that may be associated with the operations. Consider, for example, the data structure stack, which we defined earlier. In order to construct ADT stack, we would need to specify at least two basic operations called push and pop. Push will add an item to a stack and pop will remove it. Other auxiliary operations might be: top will return a copy of the top element without removing it from the stack. Size operation returns number of items currently stored in stack, and isEmpty returns true or false accordingly as stack contains at least one data element or contain more. The set of operations included in an abstract data structure is called an interface. It would follow that the elements of data structure can be manipulated only through the interface. Suppose in a program we want to access the elements of ADT stack. The program should send the request to the data structures via the interface. It can get the requested element through the interface. This is shown on the screen. It is emphasized that the operations and data items in an abstract data type are all hidden from the user. A program cannot modify the operations, nor can it add new operations to the data structure. It will be seen that all built-in primitive data types are in fact abstract data types. For example, primitive float represents a range of real numbers on which we can perform basic arithmetic operations. However, we cannot add any new operation such as exponentiation to the predefined float type. Also, we cannot enhance or modify the range of values allowed by the built-in primitive float in any particular language. It should be noted that abstract data types does not specify how the data structure and associated operations would be coded in a particular program. It also does not describe what storage structure should be used, that is, whether the data elements are stored in consecutive memory cell or in disjoint areas. In other words, abstract data structures do not provide the implementation details. The user can choose any of the several available options. For example, an ADT stack may be implemented using an array or a linked list. In a software module, ADT can be viewed as a layer between the application that uses ADT and a component that implements the ADT. This is shown on the screen. The interface of ADT remains the same regardless how the data structure and operations are actually performed. Some of the high-level languages such as C, C++, and Java have built-in features which can be used to implement a variety of ADTs. C has built-in struct type, which together with other user-defined functions can facilitate the implementation of an ADT. In C++, a class construct is available for the implementation of ADT. the class constructor creates a new ADT object. The operators can be implemented through public methods. In Java, an ADT can be expressed as interface, which is essentially an abstraction of associated operations provided by ADT. Advantages of ADT. The abstract data types have several advantages over the conventional data structures. They are reusable, robust, and consistent with well-established principles of object-oriented programming and software engineering. An abstract data type can be reused at several places in a program or in different programs. The reusability of an ADT simplifies the program design and reduces coding efforts. In abstract data type, the implementation of operations and data items are hidden from the user. Thus, encapsulation ensures that the data cannot be inadvertently corrupted by a program. Further, the working of various operations integrated into an abstract data type cannot be tampered by a program. Thus, an ADT ensures a robust data structure. Finally, the ADT approach is based on the software engineering concepts of coupling and cohesion. The coupling property determines how strongly two separate parts of a program module are mutually linked together, and the extent to which a change made in one part has impact on other parts. A well-designed software has a minimum coupling of program segments. An ADT promotes weak coupling because any change in the program or coding does not propagate to any of the components of an ADT. Cohesion property determines how well integrated are the components of a piece of software. Software engineering prescribes that good designs should maximize cohesion. An ADT inherently promotes maximum cohesion in that the ADT components are well integrated into a single compact structure.